Picture this, a landscape so vast and so high that its peaks once pierced the clouds, home to ancient forests, roaming creatures, and perhaps even the footsteps of early humans. Now imagine that entire world, every valley, every ridge, every story it held swallowed by the sea, silenced beneath miles of water, lost to time. These aren't fragments of fantasy or science fiction. They were real, they are real. Hidden below the ocean's surface lie the remains of sunken plateaus, colossal highlands that once touched the sky, and their story is one of the most breathtaking and overlooked chapters of our planet's history. For millennia, these geological titans stood as monuments to Earth's power and permanence until they weren't so permanent after all. Volcanic forces built them, tectonic shifts shaped them, and climatic upheavals drowned them, leaving behind only echoes in the form of myths, maps, and mysteries. From Plato's account of Atlantis to the submerged ruins of Doggerland, humanity has long been haunted by the idea of lands lost beneath the waves. But what if those legends weren't just metaphors? What if they were memories? This video is a journey into that very question, an exploration of the sunken plateaus that once defined continents, guided species, and anchored civilizations before vanishing into the blue. We'll travel from the deep past to the cutting edge of modern science, tracing how explorers, geologists, and dreamers have pieced together the puzzle of these drowned worlds. You'll discover how satellite technology and sonar are now revealing detailed maps of landscapes no human eye has seen for thousands of years. You'll hear how these lost highlands are not just relics, they're living records of climatic shifts, biological evolution, and human adaptation, with urgent lessons for our world today. So come with us as we dive into the depths, decode ancient secrets, and reconnect with a forgotten part of our planet's soul, because sometimes, to understand where we're going, we have to first uncover what's been buried. So what exactly are these sunken plateaus? Picture a tableland of truly epic proportions, not a single mountain, but an entire elevated region, a highland so expansive it could span thousands of kilometers, with a summit so flat and vast it could host its own unique ecosystems. These are not the jagged peaks we know today, but geological titans, formed over millions of years by the immense, restless forces shaping our planet. Deep beneath the Earth's crust, columns of superheated rock, called mantle plumes, would well up, fueling massive volcanic outpourings that built these structures layer by layer from the seafloor. In other cases, the colossal slow-motion collision of tectonic plates would thrust entire sections of continental crust upward, creating vast high plateaus. Then, over eons, wind and water would sculpt their surfaces, eroding them into those distinct, flat-topped forms we now call submarine plateaus, or sometimes, even more evocatively, drowned continents. But how does something so immense and seemingly permanent vanish beneath the waves? The process is a complex interplay of powerful geological events. One primary force is crustal subsidence. Think of it like this: these formations, often built from dense volcanic rock, are incredibly heavy. Over millions of years, their sheer weight causes the underlying oceanic crust to slowly sag and sink deeper into the malleable mantle below, like a heavy person on a trampoline. This gradual sinking is often compounded by thermal contraction. As the hot rock from their volcanic birth cools and becomes denser, then there is the factor of sea level rise. During periods of global warming, massive ice sheets on land melt, pouring enormous volumes of water back into the ocean basins, raising sea levels dramatically and drowning these already sinking landmasses. It was rarely one single cataclysm, but more often a slow, inexorable descent into the depths, a geological tragedy playing out over millennia. Geologist Dr. Maria Seton describes these submerged structures as nothing less than time capsules of Earth's climatic and biological evolution. They hold a continuous, untouched record of environmental conditions, fossilized life, and geological activity that spans ages, preserved in the deep, cold, dark quiet of the abyss. To understand this scale and significance, we can look to a real-world example, the Kerguelen Plateau. Located in the southern Indian Ocean, this sunken plateau is truly colossal, roughly the size of California, or even larger than the entire country of France. It began forming around 100 million years ago over a volcanic hotspot, and for a significant period in Earth's deep past, it was not underwater at all. It was a fully emergent continent, a land bridge connecting Antarctica and India, complete with forests, rivers, and volcanoes. Fossils retrieved from drill cores prove it was once home to lush vegetation and even dinosaurs. Its presence would have drastically altered ocean currents and atmospheric circulation patterns, and it served as a crucial migratory pathway for species, shaping the distribution of life across the southern hemisphere. This leads us to a profound and reflective question. If such immense, stable, and long-lasting geological features can be so utterly transformed, toppled from their sky-scraping heights, and consigned to the eternal night of the deep ocean, what does that tell us about the stability of our own world? The forces that shaped and then sank the Kerguelen Plateau are the very same forces that continue to operate today. By studying the clues locked in the rocks and sediments of these sunken highlands, we gain invaluable insight into the mechanics of sea level change, the patterns of species migration in response to environmental shifts, and the long-term consequences of a warming climate. Their story is a powerful reminder of our planet's dynamic nature and sets the stage for our next step, understanding how we even began to find and map these lost worlds hidden beneath thousands of meters of water. Long before sonar or satellites ever mapped the ocean floor, humanity was already telling stories about lands lost beneath the waves. These aren't mere fantasies, they are echoes, perhaps distorted by time and telling, that resonate with a startling familiarity to the geological truths we are only now uncovering. Consider Plato's detailed account of Atlantis, written in his dialogues Timaeus and Critias around 360 B.C. He describes a powerful and advanced island civilization located beyond the Pillars of Hercules, or what we now call the Strait of Gibraltar, that in a single terrible day and night of cataclysm sank into the sea and vanished. For centuries, this was dismissed as a philosophical allegory, a tale of hubris meant to teach a lesson. But what if it was more? What if it was a garbled memory passed down for thousands of years of a real geological event, a catastrophic volcanic collapse, a tsunami generated by a caldera eruption, or the final drowning of a once exposed submarine plateau like the Spartel Bank near Gibraltar, which was indeed above water as recently as 12,000 years ago. This pattern of a great flood and a lost land is not unique to Greek tradition. On the other side of the world, ancient Tamil literature in India speaks of Kumari Kandam, a vast continent that was once home to the first Tamil civilization before it was consumed by the ocean. The legends describe not one but three successive deluges that swallowed this ancient homeland, forcing a great migration and a dispersal of culture and knowledge. Historian Dr. Graham Hancock has long argued for a re-examination of these global flood myths, suggesting that such stories may not be mere inventions but could preserve a core memory of geological truths obscured by the depths of time. He posits that these are not coincidences, but a shared human recollection of a period of rapid sea level rise at the end of the last ice age, a real event that would have been catastrophic for coastal societies worldwide. The most compelling evidence that these myths are rooted in reality comes from a place where legend and archaeology have spectacularly collided: Doggerland. This was not a myth, but a very real and vast plateau that once connected Great Britain to mainland Europe. For thousands of years, it was a rich, inhabited landscape of hills, rivers, forests, and marshes, home to Mesolithic hunter-gatherers who tracked mammoths and deer across its plains. Then, as glaciers melted and seas rose, this entire world was slowly inundated. Its final death blow was likely a massive tsunami around 6150 BCE, triggered by the Storegga Slide, an underwater landslide off the coast of Norway. The waves would have been unimaginable, scouring the low-lying land and drowning it for good. Today, fishermen in the North Sea regularly trawl up ancient mammoth bones and, incredibly, finely crafted prehistoric tools from the seabed, tangible proof of a lost human landscape. The story of Doggerland is a powerful intersection of archaeology and myth. It is the physical proof of a sunken highland that was once home to people, giving credence to the idea that tales like Atlantis or Kumari Kandam could have similar origins in real, submerged lands. This forces us to ask a profound question about our own history. Could the oldest and most persistent stories we tell, the great floods, the sunken cities, the lost golden ages, actually be our species' earliest and most enduring form of historical record? Before writing, before stone monuments, we had oral tradition. Stories told around campfires, carefully passed from one generation to the next, encoding vital survival information, where we came from and what dangers to flee. A catastrophic rising of the waters that swallowed the ancestral home would be the most traumatic event a coastal culture could experience, an event so momentous it would be woven into the very fabric of their identity. These narratives, then, are not just fanciful legends. They may be the faded yet resilient memories of actual events, a prehistoric testimony to environmental change on a scale we are only beginning to appreciate. And this fascinating interplay between ancient story and modern truth sets the stage for the next chapter in our quest, the birth of oceanography and the pioneering explorers who first set out to chart these hidden depths, turning whispered myth into mapped reality. Turning myth into map required a new kind of pioneer, not with swords and ships for conquest, but with lead lines and boundless curiosity for discovery. The first great leap came from a familiar name, but for a reason many might not expect. While Charles Darwin is celebrated for his theory of evolution, his voyage on the HMS Beagle also led him to formulate a groundbreaking theory about how coral atolls are formed. Sailing through the Pacific, he was captivated by these perfect rings of life rising from the deep ocean. He correctly deduced that they were not simply growing in shallow water, but were instead the final, beautiful chapter in the story of a drowning volcano. As a volcanic island slowly sinks due to subsidence, the coral polyps surrounding it build their reefs upward, desperately keeping pace with the rising water to stay in the sunlight, eventually leaving only a lagoon-ringed atoll as the tombstone for a vanished landmass. This was a revolutionary idea that the ocean floor was not static but dynamically moving, swallowing entire mountains and leaving only a biological signature on the surface. Darwin's insight provided one of the first conceptual frameworks for understanding how the sea claims the land. But to move from theory to chart, from idea to image, required an expedition of unprecedented scale and ambition. That mission was the HMS Challenger Expedition, launched in 1872. For 3.5 years, this converted British warship sailed nearly 70,000 nautical miles, its crew tasked with the first systematic, scientific study of the global ocean. The technology they had was almost heartbreakingly simple by today's standards. To measure the profound depths, they used a technique called sounding. This involved lowering a hemp rope with a heavy weight attached until it hit the bottom, a process that could take hours for a single measurement in deep water, with the constant risk of the line snapping and losing everything. To sample the seabed, they used dredges and corers hauling up sediments from the abyss. It was grueling, monotonous work, but the rewards were earth-shattering. Among their many discoveries, the Challenger team found something astounding in the middle of the Atlantic, a seemingly continuous rise in the seafloor, a hidden mountain range they named the Dolphin Rise. This was the first hint of what we now know as the Mid-Atlantic Ridge, a discovery that would eventually help fuel the theory of plate tectonics. They had begun to map the invisible, proving the ocean floor was a landscape of immense and varied topography, not a flat, barren plain. The work of these early explorers was a testament to sheer perseverance, but the true revolution in mapping had to wait for the technological leaps of the 20th century. The advent of sonar, or sound navigation and ranging, changed everything. By emitting a ping of sound and measuring the time it took for the echo to return from the seafloor, ships could now create a continuous profile of the depth below them, a line drawing of the submerged world. This was a quantum leap from the single, painstaking measurements of the sounding line. But even with this new technology, turning those individual lines into a coherent, detailed map was a Herculean task. This is where the story of one brilliant, determined woman becomes central. Marie Tharp, a geologist and cartographer working at Columbia University in the 1950s, was handed reams of these new sonar profiles. Her job was to painstakingly compile them, line by line, into a single, coherent map of the Atlantic Ocean floor. What she began to see emerging from the data was nothing short of revolutionary. A massive, continuous mountain range running right down the center of the Atlantic, and most astonishingly, a deep, V-shaped valley cutting directly through its crest. This rift valley was the smoking gun, the first visual evidence that the seafloor was actually pulling apart, a key piece of evidence for the then controversial theory of continental drift. Her collaborator, Bruce Heason, initially dismissed the idea as girl talk, but the data was undeniable. Tharp's meticulous work didn't just map a ridge, it helped validate a theory that would completely rewrite our understanding of the planet. Her famous quote, "You can't just wish for a map, you have to go out and make it," perfectly captures the blend of daring fieldwork and painstaking analysis that defined this era. This collaborative spirit between oceanographers, geologists, and cartographers began to peel back the layers of Earth's history, one plateau at a time. A perfect example is the mapping of the Seychelles Plateau in the Indian Ocean. On the surface, the Seychelles are a picturesque archipelago of granite islands, but early depth soundings revealed something far more significant. The seafloor around them was unusually shallow and extended for hundreds of miles. This wasn't just a cluster of islands, it was the tiny, exposed tip of a vast, submerged microcontinent. By compiling soundings and later sonar data, scientists realized they were looking at a fragment of the ancient supercontinent Gondwana, a piece of continental crust that had been stranded and slowly drowned as India broke away and drifted toward Asia. Each new depth measurement was like a brushstroke, gradually revealing the full portrait of this lost world. The mapping showed it was not a random underwater feature, but a coherent geological entity with a history tied to the grandest narrative of all, the breakup of continents and the opening of ocean basins. These early efforts, from the grueling voyages of the Challenger to the detailed drafting of Tharp's maps, laid the essential foundation. They gave us the first rough sketch of the ocean's hidden topography, a sketch that we would soon begin to color in with breathtaking detail using the powerful technologies of the space age. The leap from those early, painstaking soundings to our current understanding is nothing short of a revolution in vision. For most of human history, the ocean floor was the single largest unexplored region on our own planet, a blank space on the map larger than all the continents combined. That all changed when we began to look not from ships on the surface, but from eyes in the sky. The key technology that made this possible is called satellite altimetry. It sounds complex, but the principle is beautifully simple, a testament to how gravity connects every part of our planet. It works like this. A satellite in orbit carries a highly precise radar that measures its exact distance to the ocean's surface. You might think the ocean is flat, but it's not. It has mountains and valleys of its own, subtle bulges and dips that are invisible to the naked eye. Why? Because gravity pulls water toward massive underwater structures. A colossal sunken plateau, with its immense mass, exerts a slightly stronger gravitational pull than the surrounding abyssal plain. This pulls a little more water toward it, creating a barely perceptible mound on the ocean's surface above it. Conversely, a deep ocean trench has less mass and creates a slight dip. By mapping these tiny variations in sea surface height across the entire globe, satellites like the European Space Agency's Cryosat-2 and the French-American Jason series are effectively mapping the ocean floor by proxy. They are reading the gravitational signature of the hidden landscape below. Dr. David Sandwell, a geophysicist at the Scripps Institution of Oceanography, perfectly captures the monumental impact of this, noting that these technologies are like giving us glasses to see the ocean floor clearly for the first time. It was this space-based view that allowed us to finally see the full, breathtaking scope of entire sunken continents. The most stunning example of this is Zillandia, or Te Reo a Moi in Maori. For centuries, New Zealand and New Caledonia were seen as isolated island chains, but satellite altimetry revealed the shocking truth. They are merely the highest mountain peaks of a continent almost entirely submerged. The data painted a clear picture of a vast, coherent landmass, nearly 2 million square miles in area, about 2/3 the size of Australia, with distinct plateaus, ridges, and basins. This wasn't just a collection of underwater features. It was a continent, a lost piece of Gondwana that stretched and thinned until it sank beneath the waves some 60 million years ago. The satellite gravity map was the blueprint, the broad outline that said, something enormous is down here. But to move from a blurry gravitational image to a high-definition, three-dimensional model, we needed to return to the sea with a new generation of sonic marvels. This is where multi-beam sonar enters the story, acting as the underwater equivalent of a laser scanner. Unlike the single ping of early sonar that drew one profile line at a time, a multi-beam system mounted on a ship's hull fans out hundreds of tightly focused sound beams in a wide swath across the seafloor. By measuring the precise time it takes for each of these hundreds of sound waves to travel to the bottom and bounce back, a computer can instantaneously assemble a detailed, three-dimensional point cloud of the seabed. The resolution is astonishing. Modern systems can detect features the size of a baseball on the abyssal plain or map the sheer cliff face of an underwater canyon in centimeter-level detail. This technology allows research vessels to literally paint the seafloor with sound, illuminating every seamount, every landslide scar, every ancient river valley now drowned by millennia of rising seas. When these two technologies are combined, the broad, continental-scale view from satellites and the intricate, high-resolution detail from shipborne multibeam sonar, we achieve something unprecedented. We can now visualize these sunken plateaus not as vague, mysterious blobs on a map, but as real, complex landscapes. We can trace the channels of their fossilized river systems, admire the calderas of their extinct volcanoes, and understand the tectonic forces that shaped them before their descent. This incredible power of observation inevitably brings with it a weighty responsibility and a complex set of ethical questions. The same detailed maps that allow scientists to understand ecological connections and geological history are also the very maps that mining and oil companies use to pinpoint valuable resource deposits on the seafloor. The technology itself is neutral, but its application is not. Do we use this hard-won knowledge primarily for extraction, for drilling and mining these fragile, barely understood ecosystems in the relentless pursuit of resources? Or do we prioritize its use for conservation, to identify and protect these unique underwater havens before they are disturbed, to establish marine protected areas that safeguard their biodiversity and their role as climate archives? The maps we are creating are not just charts, they are decision-making tools that will dictate the future of the largest biome on Earth. This ethical tension between discovery and exploitation, between knowledge and conservation, lies at the heart of all modern deep-sea exploration. And it is by applying these very technologies to specific, fascinating cases that we can truly appreciate both their scientific potential and the stakes involved, leading us directly to our first detailed case study. To truly grasp the monumental scale and significance of these sunken worlds, we need to focus on a specific example, and few are more impressive than the Kerguelen Plateau. Situated in the remote, storm-racked waters of the southern Indian Ocean, this is not merely an underwater feature, it is a microcontinent in its own right, a submerged realm roughly the size of California or even larger than the entire country of France. Its story begins not with a quiet whisper, but with a planetary roar around 100 million years ago during the breakup of the ancient supercontinent Gondwana. As India tore itself away from Antarctica, a massive plume of superheated rock erupted from deep within Earth's mantle, punching through the thinning crust. This was not a single volcanic event, but a prolonged, catastrophic outpouring of lava, a flood basalt eruption so immense it lasted for several million years, eventually constructing a colossal volcanic plateau that rose high above the surrounding ocean. For a significant portion of its history, the Kerguelen Plateau was not underwater at all. It was a fully emergent, vast island continent, a land unto itself. This is where its role in the grand theater of life becomes absolutely fascinating. For millions of years, this now drowned highland served as a crucial land bridge, a stepping stone for species migrating between the once connected landmasses of Antarctica and India. As these continents continued their slow, inexorable drift apart, the Kerguelen landmass remained, a stable haven in a changing world. Its climate, warmed by its volcanic nature and a more temperate global atmosphere, was capable of supporting a rich and diverse ecosystem. This is not just theoretical, we have the hard evidence pulled directly from the deep. The true turning point in understanding Kerguelen's lost world came through ambitious scientific drilling projects, most notably the ocean drilling program. Ships like the Joyd's Resolution ventured into these treacherous seas, lowered drill pipes through thousands of meters of water, and bored deep into the plateau's basalt heart. What they brought back was nothing short of revolutionary. The sediment cores contained a treasure trove of clues, layers of ancient soil, fragments of fossilized wood, and most tellingly, a rich assemblage of pollen grains and spores. These microscopic time capsules painted a vivid picture of a landscape that was once alive, a verdant world of conifer forests and flowering plants, complete with a soil ecosystem that could only have formed in open air under a sun that hasn't touched its surface for eons. Geologist Dr. Stephen Kand, who has studied the region extensively, perfectly encapsulates its importance, calling it a lost world that tells the story of Gondwana's breakup. It is a geological diary with each layer of rock and sediment recording a chapter in that epic separation, but the discoveries went even further, bordering on the cinematic. In some cores, scientists found something that seems almost unbelievable: the fossilized remains of dinosaurs. Tiny bone fragments and specific types of pollen that would have been part of the diet of large herbivorous dinosaurs suggest that this sunken plateau was not just home to insects and plants, but was once traversed by some of the most iconic creatures to ever walk the earth. Imagine that for a moment, where today there is only the crushing pressure and eternal darkness of the deep ocean. There once roamed behemoths under an open sky, surrounded by forests that grew from volcanic soil. The juxtaposition is staggering. This was a lush, habitable environment, a complete biological province that thrived for millions of years before its eventual fate. That fate was sealed by the very forces that created it. The massive weight of all that volcanic rock eventually caused the underlying oceanic crust to sag, initiating a slow, relentless process of thermal subsidence as the hot mantle rock cooled and contracted. This gradual sinking, combined with rising sea levels from a warming climate, eventually overcame the plateau's great height. The forests were drowned, the rivers were silenced, and the land that connected worlds was itself disconnected, submerged beneath the waves to become a memory preserved in stone on the ocean floor. Reflecting on this history does more than just satisfy our curiosity about the past. It provides us with a critical tool for understanding the future. By studying the rate at which Kerguelen sank and the concurrent changes in climate and sea level recorded in its sediments, we can refine our models of current global warming. It shows us the long-term consequences of a warming planet on continental margins and island ecosystems. Furthermore, by understanding how species used this land bridge for migration and then faced isolation and extinction as it sank, we gain profound insights into the vulnerability of biodiversity to geological change. The story of the Kerguelen Plateau is a powerful testament to the impermanence of even the grandest landscapes and a sobering lesson written in rock and fossil, waiting on the ocean floor. This deep dive into a single, magnificent example shows us what's possible, priming our curiosity to explore other legendary plateaus that have met a similar watery fate. While the Kerguelen Plateau tells a story of deep time and dinosaurs, another sunken highland much closer to the surface weaves a more recent and intimately human tale. This is the Mascarene Plateau, a breathtaking submerged arc that stretches for over 2,000 kilometers across the western Indian Ocean, from the granitic islands of the Seychelles in the north all the way to the volcanic peaks of Mauritius and Réunion in the south. Unlike the abyssal depths of Kerguelen, parts of the Mascarene are so shallow that sunlight still dapples their sandy bottoms, creating vast underwater savannas that make it not just a geological wonder, but a living, breathing crossroads of natural and human history. Its formation is a story of fire and ice, born from a volcanic hotspot that is still active today, fueling the fires of Réunion Island. As the Earth's tectonic plate slowly drifted northward over this stationary mantle plume, it left a trail of volcanic islands in its wake, like a geological breadcrumb trail. Over millions of years, these once mighty volcanoes cooled, eroded, and began their gradual surrender to the sea, subsiding under their own weight and from the flexing of the oceanic crust. What remains today is a sprawling, mostly submerged plateau, a chain of sunken islands, coral atolls, and incredibly shallow banks. The most spectacular of these is the Serra de Malha Bank. Located right in the middle of this submerged chain, it is the largest submerged ocean bank on our entire planet, a hidden underwater meadow the size of Switzerland. With depths as shallow as 7 meters in places, it lies dozens of meters above the surrounding abyssal plain, a sunken world that is almost, but not quite, reclaimed by the ocean. This unique shallow environment, far from any land-based silt and pollution, has allowed something extraordinary to flourish, the most extensive seagrass meadow in the world. These vast underwater pastures are not just a biological curiosity, they are a critical carbon sink and a vital nursery ground for marine life, a thriving ecosystem perched atop a drowned mountain. The presence of this vibrant life on a sunken highland immediately suggests its potential as a waypoint and resource for humans throughout history. Long before modern charts, the clues to this submerged world were written in the experiences of early mariners. Arab and European sailors, navigating these waters centuries ago in their dhows and caravels, knew of these dangers and anomalies intuitively. Their maps and logs often noted strangely discolored water, unexpected changes in depth, and the sudden appearance of certain birds far from any visible land, all telltale signs of shallow underwater features. These shoals and banks were hazards to be avoided, but they were also markers, silent proof of something large and hidden lying just beneath the waves. This historical intuition has been powerfully validated by modern archaeology. Marine archaeologist Dr. Lucy Blue, who studies such submerged landscapes, eloquently frames their significance, stating, "These plateaus are libraries of our past waiting to be read." Each artifact, each submerged site, is a volume containing stories of migration, innovation, and adaptation that we are only just beginning to decipher. The search for those stories on the Mascarene Plateau is ongoing and tantalizing. While no grand sunken city has been found, researchers have discovered compelling evidence that parts of this plateau, especially when sea levels were over 100 meters lower during the last ice age, were not just passable but potentially inhabited. The most promising evidence comes in the form of scattered lithic stone tools and flakes that have been recovered from some of the shallower banks. These aren't just random rocks, they show clear signs of human craftsmanship, of being struck and shaped by hand. The discovery of ancient pottery shards in similar contexts suggests not just temporary visitation, but more sustained activity. Could these shallow banks have served as temporary camps for ancient seafarers, a place to rest and replenish during long voyages across the Indian Ocean? It is a compelling possibility that connects the geological history of the plateau directly to the anthropological story of human expansion. This creates a fascinating interplay between the immutable forces of geology and the adaptable nature of human culture. The same volcanic hotspot that built the plateau provided the raw materials for tools like obsidian. The same subsidence that drowned it created the rich fishing grounds that would have attracted people. The plateau's physical existence created a navigational corridor, its shallow banks acting as stepping stones that may have facilitated some of the earliest long-distance voyages in human history, connecting the islands of the Western Indian Ocean into a vast interactive sphere long before the age of European exploration. It forces us to ponder a profound question. Did the very presence and subsequent drowning of this sunken highland not just record human history but actively shape it? Did it influence migration routes, cultural exchanges, and the dispersal of technologies across the ocean? The Mascarene Plateau stands as a beautiful, complex archive where the layers of geological time and the fragments of human experience are inseparably intertwined, a narrative written in rock, water, and the subtle, enduring traces of those who may have once walked its now sunken shores. And just as this hidden world supported human life, It continues to foster an astonishing abundance of marine life, creating ecological havens of breathtaking beauty and importance. Far beneath the waves, in the eternal darkness of the deep ocean, life is not just surviving, it is thriving in spectacular fashion, and it is the sunken plateaus that make this possible. These submerged highlands are not barren, empty wastelands. They are vibrant ecological havens, oases of biodiversity rising from the abyssal plains. Think of them as underwater islands, their elevated topography creating a perfect storm of conditions that support an incredible array of marine life. The mechanisms that fuel these hotspots are both elegant and powerful. First, their physical structure interrupts the flow of deep ocean currents. As these nutrient-rich waters are forced up and over the plateau's slopes, they create upwellings, bringing a constant supply of fertilizing nutrients from the depths up into the sunlit zone. This process essentially acts as a natural conveyor belt, delivering a feast of microscopic organisms that form the base of a vast and complex food web. The variety of the terrain itself is another key factor. A single sunken plateau is not a uniform flat surface. It is a complex landscape of sheer cliffs, gentle slopes, rocky outcrops, sandy plains, and ancient fossilized reefs. This mosaic of different substrates provides a perfect home for an enormous diversity of species. Hard, rocky surfaces offer a foundation for corals, sponges, and anemones to anchor themselves, while the softer sediments are ideal for burrowing creatures like worms and crustaceans. This three-dimensional complexity creates countless nooks and crannies for shelter, hunting, and breeding, supporting a density of life that far surpasses the surrounding, featureless deep sea. A prime example of this is the Lord Howe Rise off the eastern coast of Australia. This vast submerged continent is studded with seamounts and ridges that act as magnets for marine life. Scientists exploring its depths have found lush forests of ancient coral, some of which are thousands of years old, providing critical habitat for countless fish, invertebrates, and other deep-sea organisms found nowhere else on Earth. The importance of these hidden ecosystems cannot be overstated. Legendary marine biologist and oceanographer Dr. Sylvia Earle has spent decades advocating for their protection, emphasizing that these hidden highlands are critical for marine resilience and carbon sequestration. Her words highlight a dual role we are only beginning to fully appreciate. Ecologically, they are bastions of biodiversity, often hosting a high number of endemic species creatures that have evolved in isolation and exist only on that specific plateau. But they are also unsung heroes in the fight against climate change. The vast colonies of deep-sea corals and sponges, along with the sediments that accumulate around them, act as significant carbon sinks, pulling carbon dioxide out of the system and locking it away on the seafloor for millennia. To understand this in a more tangible way, we can look to the Blake Plateau, located off the southeastern coast of the United States. Recent mapping missions have revealed something astonishing. This sunken highland is home to the largest known deep-sea coral reef habitat on the entire planet. We are not talking about the shallow, sun-dependent tropical corals, but ancient cold water corals that grow slowly in the pitch black under immense pressure. These structures are breathtakingly beautiful and fragile, forming intricate gardens that provide shelter for a menagerie of unique life, from bizarre octopuses and ghostly fish to strange, never-before-seen invertebrates. These corals are masters of adaptation, having evolved to extract minute particles of food from the water column in an environment of extreme scarcity. Their very existence is a testament to life's tenacity, but it also makes them incredibly vulnerable to any disturbance. The mere drag of a single fishing trawl or the sediment plume from a mining operation could obliterate a coral colony that took centuries to grow. This brings us to a crucial and reflective crossroads. We are discovering these ecological treasure troves at the very moment they face unprecedented threats from human activity. The same rich biodiversity that makes these plateaus so vital also makes them targets for deep-sea fishing and future mining ventures seeking rare minerals. So we are left with a pressing question. In our quest for resources and knowledge, can we find a way to protect these irreplaceable underwater sanctuaries before they are lost forever? Establishing large-scale marine protected areas over these sunken highlands is not just about preserving beauty. It is about safeguarding the genetic libraries and resilience engines of our ocean. The choices we make about these hidden worlds will have profound consequences for the health of our entire planet, and remarkably, the very sediments that blanket these plateaus hold another kind of library altogether, one that archives the entire history of Earth's climate. Beneath the crushing silence of the deep ocean, the sunken plateaus hold a library, but this isn't a library of books. It's a vast, layered archive written in mud, stone, and the microscopic shells of long-dead creatures. For paleoclimatologists, scientists who study Earth's past climates, these submerged highlands are the closest thing we have to a time machine. The process begins over millennia as a constant, gentle rain of particles settles onto the plateau's surface. This marine snow consists of everything from dust blown off distant continents and ash from volcanic eruptions to the tiny skeletal remains of plankton that once lived in the sunlit waters far above. Layer by imperceptible layer, this material accumulates, burying and preserving a continuous record of the conditions at the time it fell. By drilling deep into these sediment piles and extracting long, cylindrical cores, scientists can literally hold a vertical timeline of Earth's history in their hands, reading the planet's story backwards through time. The science of extracting this information is both intricate and brilliant. Researchers analyze the chemical composition of the ancient water trapped in the sediment pores, and they study the isotopic signatures in the fossilized shells of foraminifera, tiny plankton that absorbed the ocean's chemistry while they were alive. The ratio of different oxygen isotopes, for instance, acts as a precise thermometer, revealing the temperature of the ancient ocean and the volume of water locked away in ice sheets. If they find a layer rich in a specific isotope, it points to a cold period, a global ice age. A shift in the ratio signals a warming event, the melting of glaciers and a rise in sea level. These cores can also trap tiny bubbles of ancient atmosphere, snapshots of what the air itself was composed of hundreds of thousands of years ago, allowing us to measure past concentrations of greenhouse gases like carbon dioxide and methane with astonishing accuracy. A stunning example of this detective work comes from the Newfoundland Ridge, a submerged plateau off the coast of Canada. Drilling projects here have pulled up cores that tell a dramatic story of the ocean's conveyor belt, the great global current system that redistributes heat around the planet and is crucial for regulating our climate. The sediments revealed layers of coarse, rocky debris that could only have been transported and dropped by powerful, deep-reaching currents. By dating these layers, scientists discovered that these currents have dramatically slowed down or even shut down entirely during past periods of rapid climate change. This shutdown would have caused catastrophic shifts in weather patterns, plunging some regions into deep cold while overheating others. This data from the deep is not just about the past, it provides a critical benchmark. It shows us the specific conditions, the precise levels of atmospheric CO2 and global temperature that triggered these disastrous oceanic collapses in the past. This allows us to compare those ancient thresholds to the changes we are causing today, offering a terrifyingly clear warning. This is why climate scientist Dr. James Hansen, a pioneer in the field, has long emphasized that these underwater records are essential for validating our climate models and predicting future trends. Our computer models of the climate system are incredibly complex, but they are just that, models. They are built on equations and physics. The data from Sunken Plateaus provide the ground truth. They are the real-world experiments, the historical outcomes that show us what actually happened when the planet was pushed past certain points. If a model can accurately predict the changes we see recorded in a sediment core from 200,000 years ago, we can have far more confidence in its predictions for the next 100 years. Further afield, the Agalas Plateau in the South Atlantic offers another powerful chapter in this climatic archive. This massive underwater structure acts like a bathtub ring, recording the dramatic seesaw of sea levels over millions of years. Its sediments are particularly rich in fossils of a specific type of plankton that is highly sensitive to water temperature. By analyzing these layers, scientists have been able to reconstruct detailed records of past global warming events that bear a striking resemblance to what we are experiencing now. The data shows not just the temperature spikes, but the subsequent ocean acidification and shifts in ecosystem structures that followed. It reveals how quickly the climate system can flip from one stable state to another, and how long it takes to recover. These are not abstract data points. They are a direct physical record of the consequences of a planet out of balance. This knowledge fundamentally informs our current climate policies and the urgent international debates surrounding them. The data from these sunken archives moves the conversation from theoretical projections to historical fact. It tells us that the changes we are initiating have precedent and that the outcomes were severe. It provides the hard evidence that underpins the reports of the Intergovernmental Panel on Climate Change (IPCC), translating complex model outputs into a narrative grounded in Earth's own history. When we talk about aiming to limit global warming to 1.5 or 2 degrees Celsius, those aren't arbitrary numbers. They are thresholds informed by the very real climatic tipping points identified in these deep-sea sediment cores. They represent the difference between a manageable shift and a catastrophic reorganization of our planet's systems, as recorded in the mud of the ocean floor. This profound understanding of past change pulled from the depths makes the next question unavoidable. What immense forces could actually cause these colossal, record-keeping highlands to sink beneath the waves in the first place? The descent of these once majestic highlands into the ocean's abyss was not a single catastrophic event, but a complex symphony of geological processes playing out over millions of years, a slow-motion drama of shifting rock, changing climates, and rising waters. To understand the Great Submersion, we need to think like the planet itself, on a scale of both immense power and patient, grinding time. The first and perhaps most fundamental force is tectonic subsidence. Imagine the Earth's crust not as a rigid, unyielding shell, but as a flexible layer floating on a denser, viscous mantle beneath. When a massive volcanic plateau like the Kerguelen forms from countless lava flows, it places an enormous new load on the oceanic crust. This is like placing a heavy weight on a soft mattress. The crust responds by slowly, inexorably sagging downward over millennia. This process, known as isostatic adjustment, is the crust's way of seeking a new balance. The sheer weight of the rock literally pushes the crust deeper into the malleable mantle, dooming the plateau to a gradual, inescapable descent. But the story doesn't end with the crust simply bending under pressure. There's also the factor of thermal subsidence. When a plateau is born from a superheated mantle plume, the rock is initially extremely hot and therefore less dense. As millions of years pass, this rock cools down, contracts, and becomes denser. This increase in density causes the entire formation to sink further, like a cooling cake settling after being taken out of the oven. This combination of isostatic and thermal subsidence sets the stage, slowly lowering the elevation of these vast highlands and bringing them ever closer to sea level. It's a relentless background process of sinking that primes the landscape for its final drowning. Then comes the water itself. While the crust is slowly sinking, the level of the global ocean can be rising to meet it. This is called eustatic sea level change, and its primary driver over the last few million years has been the dramatic expansion and contraction of massive continental ice sheets during ice ages. During a glacial period, like the last one that peaked around 20,000 years ago, so much of the planet's water is locked up in ice sheets miles thick over North America and Eurasia that global sea level can be over 120 meters lower than it is today. This exposed vast stretches of the continental shelves, turning what are now shallow seas into dry, habitable land. The Sunda Shelf in Southeast Asia is a perfect case study. During the last glaciation, this wasn't a shelf at all. It was a sprawling, low-lying plain known as Sunderland, connecting the islands of Indonesia, Borneo, and Java to the Asian mainland. It was a rich, tropical landscape crossed by great rivers, home to tigers, rhinos, and early human populations. The end of an ice age, however, is a period of breathtakingly rapid change. As global temperatures rose, those colossal ice sheets began to melt, pouring trillions of gallons of meltwater back into the ocean basins. This wasn't a gentle, uniform rise. Geophysicist Dr. Jerry Mitrovica and his team have revolutionized our understanding of this process, revealing that sea level rise is far from uniform across the globe. Their work shows that the melting of immense ice sheets like the one that covered North America actually changes the Earth's gravitational field and rotation. The loss of all that ice mass reduces its gravitational pull on the surrounding ocean water, meaning sea level might actually fall near a melting ice sheet while rising dramatically on the other side of the world. Furthermore, the weight of the ice had been pressing down on the continents, and as it melted, the land itself began to rebound upward in a process called glacial isostatic adjustment, which also locally affects relative sea level. This creates a complex seesawing pattern of ocean rise and fall across the planet, a far cry from the simple image of a bathtub filling evenly. For a place like the Sunda Shelf, the result was inevitable and transformative. The combination of the global influx of meltwater and the ongoing subsidence of the shelf itself led to a rapid and relentless invasion of the sea. The Great Plains of Sunderland were inundated, river valleys became straits, and mountain peaks were isolated into the islands we know today. This drowning wasn't just a geological event, it was a cultural and ecological cataclysm. It would have forced the human populations living there into a constant, desperate retreat, fragmenting communities, severing trade routes, and forever altering the course of history in the region. The myths of lost lands in this part of the world are not just stories, they are the cultural memory of a real, witnessed disaster. This deep history forces us to look at our own world with a new and urgent perspective. The same processes that drowned the Sunda Shelf and the Sunken Plateaus are still operating today. The thermal and isostatic subsidence of ocean crust continues, a slow, unstoppable geological heartbeat. And now, human-induced climate change is triggering a new era of rapid eustatic sea level rise through the melting of glaciers and ice sheets in Greenland and Antarctica. We are, in effect, accelerating one part of the ancient recipe for submersion. The lessons from the past are clear. When the land sinks and the seas rise, the consequences for life, human and otherwise, are profound and permanent. The great forces of geology are indifferent to our presence. They simply proceed, understanding their interplay is not just an academic exercise, but a critical key to anticipating the changes already lapping at our shores. The drowning of these vast highlands was far more than a geological event. It was a profound human drama that reshaped the very course of our history, forcing adaptations whose echoes we still feel today. As the seas rose, inch by relentless inch over centuries, they did not simply erase land. They rewrote maps of human existence, pushing populations into motion and acting as a powerful engine for migration, cultural exchange, and ultimately, innovation. For the communities living on these fertile coastal plains and plateaus, the change was not abstract. It was a slow-motion emergency, a constant, encroaching reality that demanded response. Each generation would have witnessed familiar hunting grounds shrinking, freshwater sources becoming brackish, and ancestral villages being gradually abandoned to the waves. This was not a single, catastrophic flight, but a long, strategic retreat that required immense resilience and forced a constant recalibration of survival strategies. The story of Doggerland, the now submerged plateau in the North Sea, provides our most vivid window into this process. For millennia, this was not a sea but a rich, low-lying land bridge connecting Britain to continental Europe, a paradise for Mesolithic hunter-gatherers teeming with game, fish, and forests. As the climate warmed after the last ice age and meltwater poured into the oceans, these communities faced an existential threat. Archaeologists, piecing together evidence from dredged-up animal bones and human tools, can trace their retreat. They didn't vanish, they moved, likely in stages, following the migrating herds and the receding coastline towards the higher grounds of what are now Britain and the Netherlands. This great displacement was not merely a change of address. It forced a density of population in these new areas, increasing competition for resources and inevitably sparking new social dynamics, conflicts, and collaborations. Crucially, this concentration of people and knowledge in refugee communities became a melting pot for ideas. The pressure to adapt likely accelerated technological innovations in tool-making, boat building, and new foraging techniques to exploit marine resources more efficiently. This idea that catastrophe can breed progress is central to the work of anthropologist Dr. Brian Fagan, who reframes these ancient events not as simple tragedies but as transformative forces. He argues these drownings were not just disasters, they were catalysts for human innovation and dispersal. The need to navigate rising waters undoubtedly spurred the development of more sophisticated watercraft. The displacement of populations broke down cultural isolation, forcing the exchange of languages, technologies, and mythologies across vast distances. The stories and skills carried by the refugees from Doggerland would have rippled across Neolithic Europe, influencing the cultures they joined and transformed. This pattern of displacement-driven innovation is a recurring theme in human history, where environmental pressure forces a leap in adaptability. Nowhere is this legacy of maritime adaptation more evident than in the vast expanse of the Pacific Ocean. Across countless islands, from the Philippines to Tahiti, oral histories are rich with stories of great floods and lost lands, echoing the geological truth of drowned coastlines and submerged archipelagos as sea levels rose. The most remarkable responders to these changes were the Lapita people, the incredible seafaring ancestors of many Polynesian cultures. While their voyages were driven by many factors, the gradual inundation of coastal habitats and the loss of land would have been a powerful motivator to take to the open ocean in search of new beginnings. Their response wasn't just retreat, it was a breathtakingly bold expansion. Developing revolutionary double-hulled voyaging canoes and mastering sophisticated navigation by stars and waves, they didn't just flee the rising water, they conquered it. They spread across the Pacific, carrying with them a distinctive culture, language, and toolkit, effectively using the ocean not as a barrier but as a highway. Their story is the ultimate testament to human resilience in the face of a changing world, showing how a threat can be transformed into an opportunity for unparalleled exploration and cultural dissemination. This deep history carries a sobering and urgent resonance for our world today. The scenes we reconstruct from Doggerland and the Pacific are not confined to the distant past. They are a precursor to the challenges faced by modern coastal communities from Bangladesh to the Pacific Islands. The slow, inevitable rise of sea levels today is creating a new generation of climate refugees, people forced to abandon their homes, their histories, and their ways of life due to encroaching saltwater. The same human stories of loss, resilience, and difficult migration are playing out on a global scale, reminding us that the relationship between humanity and the sea is as dynamic and fraught as ever. Understanding how our ancestors adapted to the drowning of their worlds is more than an academic exercise. It is a crucial lesson in human endurance that informs how we might humanely and wisely manage the great displacements of our own future. This profound connection between sunken lands and human movement naturally leads us to consider what else these lost landscapes hold, shifting our focus from cultural history to the tangible resources that make these submerged realms the focus of intense economic interest. Beneath the serene, dark waters that now cover these lost worlds lies a treasure trove of immense economic value, a potential fortune that places the Sunken Plateaus squarely at the center of one of the most pressing dilemmas of our time: the conflict between resource hunger and environmental preservation. These submerged highlands are not just geological wonders and biological havens. They are also storehouses of the very minerals and energy sources that power our modern civilization, making them irresistible targets for extraction industries. The list of riches is staggering. Thick layers of sediment that accumulated over millions of years have created perfect conditions for the formation of oil and natural gas, trapping hydrocarbons in porous rock capped by impermeable clay. Beyond fossil fuels, the cold, high-pressure plains of these plateaus are littered with polymetallic nodules, potato-sized lumps rich in manganese, nickel, copper, and cobalt, metals essential for everything from stainless steel to the batteries in our electric vehicles and smartphones. In some regions, particularly around hydrothermal vents that dot these underwater landscapes, crusts rich in rare earth elements can be found, a group of 17 metals critical for manufacturing high-tech devices, wind turbines, and military hardware. The geological processes that create these resources are as fascinating as they are profitable. Take, for instance, the Rio Grande Rise, a massive submarine plateau in the South Atlantic Ocean off the coast of Brazil. This structure began as a volcanic hotspot, much like the Kerguelen Plateau, but over eons it became blanketed in layers of sediment. As microscopic marine organisms died and settled on the seafloor, their organic remains were slowly cooked by the Earth's heat and pressure under the weight of accumulating sediment, transforming over millions of years into pockets of oil and gas. These hydrocarbons migrated upward through the porous rock until they were trapped by a seal of denser, non-porous rock, forming a reservoir just waiting to be tapped. To access these deep-sea riches, companies use incredibly sophisticated and expensive technology. Drill ships, stabilized by dynamic positioning systems that use thrusters to hold them steady over a single spot in the open ocean, lower drill strings through miles of water before boring even further into the seabed. Remotely operated vehicles, or ROVs, are the robotic workhorses of these operations, performing intricate tasks like connecting pipes and monitoring equipment in the crushing darkness. This drive to exploit is met with equally powerful concerns about the irreversible damage such activities could inflict. The debate over the Chukchi Plateau in the Arctic Ocean is a perfect microcosm of this global conflict. This region is believed to hold vast, untapped reserves of oil and gas, a prospect that has drawn intense interest from energy companies and nations bordering the Arctic. However, drilling in this environment presents unparalleled risks. The extreme cold, the presence of sea ice for much of the year, and the remoteness of the location make any potential oil spill a catastrophe that would be nearly impossible to contain or clean up. The Arctic ecosystem is particularly fragile and slow to recover, and a spill could devastate the marine life that indigenous communities and local predators like polar bears depend on for survival. The very act of prospecting, using intense air guns for seismic surveys, has been shown to disorient and harm whales and other marine mammals that rely on sound for navigation and communication. This tension between economic gain and ecological responsibility is at the heart of the warning from environmental economist Dr. Samantha Smith, who states that balancing resource exploitation with ecosystem protection is the challenge of our century. Her perspective highlights the core of the issue. These are not just technical or economic problems, but profound ethical ones. On one hand, the metals found in manganese nodules and crusts are vital for the global transition to green energy. We need cobalt for electric vehicle batteries and rare earth elements for efficient wind turbines. It can be argued that mining them from the deep sea could be less destructive than the often devastating land-based mining for these same resources, which can lead to deforestation, human rights abuses, and the pollution of freshwater systems. On the other hand, the deep-sea ecosystems on these plateaus are some of the least understood on Earth. We are only beginning to discover the strange and unique life forms that thrive there, and many scientists argue that destroying these habitats for their minerals is like burning down a library before we have even read the books. The operations themselves could create immense sediment plumes that would smother life across vast areas of the seafloor, and the noise and light pollution would disrupt behaviors in species we are only just beginning to study. This leaves us with a series of difficult, unresolved questions that society must grapple with. Do we have the right to exploit these resources simply because we have the technology to do so? How do we weigh the immediate economic benefits and technological progress against potential, long-term environmental losses that may be irreversible? Is the concept of sustainable use even applicable in an environment where life grows so slowly and recovery from disturbance could take centuries or millennia? And who gets to make these decisions? The answers are not simple, but they force us to define what kind of relationship we want to have with the last great wilderness on our planet. This ethical quandary over who owns these resources and who has the authority to permit or forbid their extraction inevitably pulls us into the complex and often contentious world of international law and politics, a realm where national ambition collides with the ideal of the deep ocean as a common heritage for all humankind. This complex web of economic and environmental interests inevitably leads to a fundamental question: who actually owns these sunken plateaus and the riches they contain? The deep ocean floor was long considered a global commons, a space beyond national jurisdiction belonging to everyone and no one. But as technology has advanced and the value of underwater resources has skyrocketed, this vast frontier has become the stage for intense legal and political battles, where nations jockey for control using a complex framework of international law. The primary rulebook for this modern-day scramble is the United Nations Convention on the Law of the Sea, or UNCLOS. This monumental treaty, often called the Constitution for the Oceans, was finalized in 1982 and has been ratified by most of the world's nations. It provides the essential legal architecture that divides the ocean into different zones of national authority and shared use. The most crucial concept for understanding the fate of sunken plateaus is the extended continental shelf. Under UNCLOS, every coastal nation automatically has control over the resources on and under its continental shelf, the natural, shallow extension of its landmass underwater, typically out to 200 nautical miles from its shore. However, if a nation can provide detailed scientific and geological data proving that its continental shelf extends even further naturally, it can submit a claim to the UN for an extension, granting it exclusive rights to the resources on that seabed out to a maximum of 350 nautical miles. This is where sunken plateaus become geopolitical gold. For many countries, these massive submerged structures are not isolated seafloor features. They are integral, physical parts of their continental landmass now drowned. Proving that geological connection is the key to unlocking sovereign rights over vast, resource-rich territories. Nations like Russia, Canada, Australia, and France have invested millions of dollars and years of effort into mounting sophisticated mapping expeditions, using icebreakers, research vessels, and submarines to gather the bathymetric and seismic data needed to substantiate their claims. Russia famously planted a titanium flag on the seabed at the North Pole in 2007, a dramatic, if legally symbolic, stunt to bolster its claim that the Lomonosov Ridge, a 1,200-mile-long underwater mountain range, is an extension of its continental shelf. Legal scholar Dr. Robin Churchill underscores the immense stakes of this process, pointing out that these are not just legal technicalities, they shape global geopolitics and environmental governance. A successful claim doesn't just grant mining rights, it extends a nation's sovereignty, influencing everything from military strategy to scientific research permissions. These extended claims can create massive, overlapping zones of contention between neighboring nations. Nowhere is this more evident than in the South China Sea, a region fraught with tension where the legalities of UNCLOS collide with powerful nationalistic ambitions. Several submerged plateaus and reefs, such as the Spratly Islands and the Scarborough Shoal, are claimed in whole or in part by multiple countries including China, Vietnam, the Philippines, and Malaysia. These are not disputes over barren rocks, they are battles for control over some of the world's most vital shipping lanes, rich fishing grounds, and potentially enormous oil and gas reserves trapped in the seabed below. China's assertive construction of artificial islands and military bases on these submerged features is a clear attempt to solidify its claim by establishing a physical presence, a tactic that other nations view as a direct challenge to the international legal order. These disputes reveal the immense challenge of governing the global commons. While UNCLOS provides a framework, it lacks a powerful enforcement mechanism. The peaceful resolution of these conflicts depends heavily on diplomacy, negotiation, and sometimes the adjudication of international tribunals. It forces us to consider whether the current system, which often pits nation against nation in a race to claim and exploit, is the best way to manage these shared resources for the benefit of all humanity, or if it inevitably leads to conflict and environmental degradation. The outcome of these legal battles will determine not only who profits from the deep sea, but also who is responsible for protecting its fragile ecosystems from harm. This high-stakes game of mapping and claiming these remote territories underscores just how difficult they are to access, pushing the very limits of technology and human endurance to even reach them, let alone manage them responsibly. Venturing into the realm of the sunken plateaus is one of the most formidable engineering challenges humanity has ever undertaken. a mission that demands we conquer an environment more hostile than the surface of the moon. The crushing pressures, the perpetual darkness, and the sheer, mind-boggling scale of the deep ocean require a suite of robotic and human-operated marvels, each designed to act as our eyes, hands, and senses in the abyss. The workhorses of this modern exploration are of two distinct types: the autonomous underwater vehicles, or a UVS, and the remotely operated vehicles, or ROVs. An ROV is essentially a robotic submarine, a self-piloting drone programmed to embark on solo missions. It might spend 24 hours or more gliding over a sunken plateau in a precise grid pattern, using multi-beam sonar and other sensors to map the terrain with breathtaking resolution, all while its human operators wait on a ship at the surface, completely out of contact until it returns to upload its precious data. The ROV, by contrast, is a tethered extension of human will, connected to the mothership by a thick, armored umbilical cable that provides power and allows for real-time data transmission. These robotic platforms are steered by pilots using joysticks and high-definition video feeds. They are the precise surgeons of the deep, equipped with manipulator arms that can collect a delicate biological sample with the care of a jeweler or deploy a multi-ton scientific instrument onto the seafloor. The design and operation of these machines is a constant battle against physics. At a depth of 4,000 meters, a typical depth for many plateaus, the pressure is a staggering 400 times greater than at the surface. That is equivalent to having an entire SUV pressing down on every single square inch of the vehicle's frame. A pinhole leak or a minor electrical short at this pressure would mean instant and catastrophic failure. To withstand this, the vehicle's electronic brains and camera housings are encased in specially engineered titanium or ceramic spheres, each one tested and retested to ensure not a single molecule of water can penetrate. The legendary ocean explorer Dr. Robert Ballard, who has personally overseen the development of some of the world's most advanced ROVs, perfectly captures the spirit of this endeavor, noting that each dive is a step into the unknown, pushing the limits of technology and human curiosity. His words remind us that every mission is a high-stakes gamble, sending millions of dollars of sophisticated equipment into a realm from which it might not return, all for the chance to catch a fleeting glimpse of something never before seen by human eyes. Beyond the robotic explorers, there are the massive, globally operated drilling ships like the Droid's Resolution. These are floating cities of science, capable of holding their position against wind and wave using dynamic positioning systems that fire thrusters with computer-guided precision. They lower drill strings through miles of water before then penetrating hundreds of meters into the seabed itself, extracting the deep sediment cores that serve as our primary windows into Earth's climatic past. The logistical symphony of keeping a research vessel operational for months at a time in the remote, stormy seas above these plateaus is a monumental achievement in its own right. One of the most dramatic examples of pushing these technological frontiers was the series of expeditions to the Glacial Ridge, a massive and deeply buried mid-ocean ridge beneath the ice-covered Arctic Ocean. Mapping this ultra-slow spreading ridge was a task many thought impossible. The challenges were unprecedented, navigating through dense sea ice that could easily crush a ship, operating robotic vehicles through small, temporary holes melted in the ice, and maintaining communication in such a hostile, remote environment. Yet, using a combination of icebreakers, specially hardened UVS, and immense determination, scientists did the impossible. They not only mapped sections of the ridge in stunning detail but made a breathtaking discovery: entire fields of hydrothermal vents, or black smokers, spewing mineral-rich water at temperatures exceeding 300 degrees Celsius, supporting lush ecosystems of unique life in the absolute darkness under the ice cap. This discovery, made possible only by the most advanced technology, fundamentally expanded our understanding of where life could exist on our planet and potentially on others. These continuous breakthroughs force us to look ahead and ask what the next generation of deep-sea exploration might hold. Will we develop autonomous robots that can swarm a sunken plateau, working in coordinated fleets to map enormous areas in a fraction of the time? Could we create new, bio-inspired materials that are both stronger and more flexible to better withstand the immense pressures? Might we see the development of permanent, manned observatories stationed directly on the seafloor, allowing for continuous, long-term study of these dynamic environments, much like the International Space Station does for the vacuum above? The technological frontiers are constantly expanding, each solved problem revealing a dozen new and even more fascinating mysteries waiting in the darkness, mysteries that beckon with the promise of rewriting our understanding of the planet and our place within it. For all the incredible discoveries we've made on these sunken highlands, they remain home to some of the ocean's most tantalizing and enduring enigmas, puzzles that challenge our understanding of both geology and human history, and invite us to wonder what secrets might still be lurking in the unlit depths. These are not just unanswered questions, but anomalies, features, and formations that seem to defy easy explanation, sitting in that intriguing gray area between the known and the utterly mysterious, prompting both rigorous scientific inquiry and more speculative, controversial theories. Perhaps the most famous and hotly debated of these is the Yonaguni Monument. Located off the coast of Yonaguni Island in Japan, this massive underwater structure was discovered by a diver in the 1980s. It consists of a series of immense monolithic sandstone blocks that appear to form a grand, terraced complex. The surfaces are strikingly flat, the edges are sharp and precise, and the entire formation features what look like staircases, platforms, and even two massive, pillar-like stones that appear to be placed parallel to each other. To many observers, the sheer geometry and apparent symmetry of the site feel undeniably architectural, as if carved and arranged by intelligent hands. The fact that it lies in an area that was unquestionably above sea level until the end of the last ice age only fuels the fire of speculation, suggesting that if it is artificial, it would be a relic of a prehistoric culture that thrived over 10,000 years ago, a time when mainstream archaeology tells us humans were simple hunter-gatherers. This line of thinking leads to one of the most controversial ideas surrounding sunken plateaus, the possibility that they were once home to pre-advanced civilizations, sophisticated societies that were completely wiped from the historical record when their homelands were consumed by the rising seas. This theory suggests that the rapid flooding at the end of the last ice age was so catastrophic that it effectively reset human civilization, drowning not just land but entire cultures and their achievements. Researchers like Dr. Rand Flem-Ath have championed variants of this idea for decades, proposing that the lost continent described by Plato as Atlantis might have been a real memory of such a civilization, and that its survivors scattered across the globe, seeding knowledge and jump-starting the development of ancient cultures in Egypt, Mesopotamia, and the Americas. Proponents of this view point to the sheer number of global flood myths as collective memory of this event, and argue that enigmatic structures like Yonaguni, or the seemingly arranged stone blocks off the coast of Cuba at a depth of over 600 meters, could be the physical evidence we've been missing, the ruins of a world lost to the Great Inundation. However, the mainstream scientific community approaches these claims with profound and necessary skepticism. The overwhelming majority of geologists and archaeologists who have studied sites like Yonaguni attribute them to entirely natural processes. They point out that the sandstone in the region is crisscrossed with natural horizontal and vertical bedding planes and joints, which, when exposed to powerful underwater currents and erosive forces, can fracture and weather into incredibly regular, block-like formations. The seemingly flat surfaces and sharp edges can be explained by the way the rock shears along its natural lines of weakness. Geologist Dr. Lisa McNeil, who specializes in marine geology, offers a crucial perspective that helps navigate this divide between mystery and overreach. She advises that we must distinguish between compelling mystery and pseudoscience. The ocean floor is full of bizarre and beautiful formations that challenge our immediate perception. Our job is to apply rigorous methodology, not to jump to the most sensational conclusion. Her point is vital. The natural world is capable of producing shapes of breathtaking regularity and apparent design without any human intervention. The process of concretion, for instance, can create near-perfect spherical stones. Columnar basalt forms hexagonal pillars that look meticulously crafted. To a trained geologist, Yonaguni bears all the hallmarks of a fantastic, but entirely natural geological phenomenon. This doesn't make the site any less significant or fascinating. It simply shifts the wonder from the realm of archaeology to the awe-inspiring power of natural geology. The real mystery of Yonaguni may not be who built it, but how the precise interplay of rock composition, tectonic activity, and marine erosion could create something that so perfectly mimics the hallmarks of intelligent design. This balanced approach, maintaining an open mind to extraordinary possibilities while demanding extraordinary evidence, is the very heart of the scientific method. It encourages a healthy, open-minded inquiry that is willing to follow the evidence wherever it leads, but is also disciplined enough to resist the seductive pull of a convenient narrative when the data doesn't support it. These unresolved debates, far from being a weakness of the field, are actually a sign of its health and vitality. They represent the cutting edge of exploration, the frontier where known science meets the vast unknown. They force us to ask better questions, to develop new technologies for investigation, and to continually re-evaluate our assumptions about the past. And this spirit of inquisitive preservation is more critical than ever, because whether these sites are natural wonders or cultural treasures, they are equally fragile and irreplaceable, and their greatest mystery might be lost forever if we are not careful to protect them. Yet for all their resilience and ancient grandeur, the breathtaking ecosystems thriving on these sunken plateaus face a new and unprecedented threat, one they did not evolve to withstand: us. The very technologies that have allowed us to discover and marvel at these hidden worlds are now being turned toward their potential exploitation, creating a conservation challenge as vast and deep as the oceans themselves. The primary dangers are stark and multifaceted. Deep-sea mining poses perhaps the most immediate and severe risk. Companies are actively developing massive machinery designed to travel across the seafloor, vacuuming up polymetallic nodules or stripping mineral-rich crusts from the slopes of these plateaus. The process is brutally destructive. It would not only obliterate every living thing in its direct path, but also generate immense, suffocating plumes of sediment. These clouds of fine particles could drift for hundreds of kilometers on deep-sea currents, smothering fragile filter-feeding organisms like corals and sponges, clogging their feeding apparatuses and effectively starving them to death across an area far greater than the mining site itself. The noise and light pollution from such industrial activity would further disrupt the behaviors of deep-sea creatures that have evolved over millions of years in a world of silence and perpetual darkness. Alongside mining, the pervasive practice of bottom trawling continues to inflict terrible damage. This fishing method involves dragging heavily weighted nets across the seafloor to catch species like grenadiers and orange ruffy that dwell near the bottom. These nets do not discriminate. They scrape and crush everything in their path, leveling ancient coral forests that have taken thousands of years to grow and destroying complex habitats in a single pass. The Blake Plateau off the southeastern United States provides a sobering case study. Despite being home to the planet's most extensive deep-sea coral ecosystem, large swaths of it have been scarred by decades of trawling activity. Sonar maps reveal vast areas where the complex, three-dimensional coral gardens have been flattened into barren mud plains, a tragic loss of biodiversity and a stark warning of what could happen elsewhere without stringent protection. Furthermore, pollution from the surface world eventually finds its way into the deep. Plastics break down into microplastics that are consumed by deep-sea organisms, and toxic chemicals from industrial runoff and agricultural waste can accumulate in the food web, poisoning creatures that have never known sunlight. In the face of these threats, a global movement is growing to safeguard these irreplaceable deep water sanctuaries before it's too late. The most powerful tool in this effort is the establishment of large-scale marine protected areas, or MPA. These are legally designated zones where harmful extractive activities like mining and bottom trawling are strictly prohibited or severely limited, allowing ecosystems to recover and thrive. The single most ambitious success story is the Papahanaumokuakea Marine National Monument in the northwestern Hawaiian Islands. Enlarged in 2016 to over 1.5 million square kilometers, it is one of the largest protected areas on Earth. This vast MPA encompasses not just islands and shallow reefs, but also protects the immense deep-sea plains, seamounts, and sunken plateaus that surround them, creating a safe haven for everything from migratory whales to strange, endemic creatures of the abyss. Its establishment was the result of a remarkable collaboration between scientists, native Hawaiian cultural practitioners, and political leaders, demonstrating that conservation on a grand scale is achievable. These protected areas are often bolstered by international agreements. Bodies like the International Seabed Authority are tasked with regulating mining in international waters, while regional fisheries management organizations can vote to close vulnerable marine ecosystems to destructive fishing practices. However, these efforts are a constant race against economic and political pressure. The poignant words of National Geographic explorer in residence Dr. Enric Sola resonate deeply here. We are racing to protect what we have not yet fully understood. His statement cuts to the heart of the dilemma. We are still in the earliest stages of discovering the life forms and complex ecological relationships that exist on these sunken highlands. Every single research dive brings up species new to science, and we are only beginning to grasp how these ecosystems function and their role in the broader health of the ocean, from carbon sequestration to nutrient cycling. To destroy them for short-term gain is to irrevocably erase a chapter of our planet's biological history before we have even read it. This immense responsibility forces us to confront a profound ethical question. Do we as a species have the right to alter and destroy these ancient, fragile ecosystems that have taken millions of years to develop, simply because we possess the technological capability to reach them? Or do we have a moral obligation to act as stewards, to exercise restraint and ensure that these hidden worlds remain pristine, not as a resource to be extracted, but as a legacy to be understood and preserved for future generations? The answer to that question will define our relationship with the last great wilderness on Earth, and it is a question that has already begun to spark the human imagination in powerful and creative ways. inspiring a wave of cultural expression that translates scientific wonder into universal stories. The allure of these vanished worlds extends far beyond the realms of science and law, seeping deeply into the very core of our collective creativity. There is something profoundly resonant about the concept of a lost land, a sunken realm that exists just beyond our grasp, and this potent blend of mystery, tragedy, and wonder has fueled the human imagination for centuries, giving rise to some of our most enduring stories and artworks. This fascination often manifests as a powerful thematic undercurrent, a deep-seated yearning to explore the unknown and to ponder what or who might have been lost to the relentless march of time and tide. The Sunken Plateau, in all its inaccessible grandeur, becomes the perfect metaphorical canvas for exploring these universal themes of loss, curiosity, and the enduring human spirit. We can trace this cultural thread back to some of the foundational works of modern adventure literature. Jules Verne's seminal 1870 masterpiece, 20,000 Leagues Under the Sea, is arguably the quintessential example. Captain Nemo's incredible journey aboard the Nautilus doesn't just take him through the ocean, it takes him through a landscape of the imagination, one that was directly informed by the new and thrilling discoveries of the HMS Challenger Expedition. Verne's descriptions of the lost, submerged continent of Atlantis are not merely set dressing, they are a central pillar of the story's mystique. He portrays it not as a barren wasteland, but as a haunting, beautiful graveyard of a civilization, complete with crumbling volcanic ruins and silent, ghostly fields of lava. For Verne, the deep ocean was the ultimate frontier, and the sunken highland was its most majestic and melancholy monument, a symbol of nature's awesome power to erase even the mightiest of kingdoms. This artistic legacy has been powerfully carried into the modern era by filmmakers who are themselves pioneers of deep-sea exploration. Director James Cameron, who has personally descended to the deepest point on the ocean floor in the Mariana Trench, has repeatedly woven these themes into his most iconic films. In Avatar, the floating Hallelujah Mountains of Pandora are a direct and breathtaking visual homage to the concept of sky-touching highlands, reimagined through a science fiction lens. They capture that same sense of majestic, impossible geography that feels both ancient and awe-inspiring. His blockbuster, Titanic, is at its heart a story about a lost world rediscovered, a grand, sunken artifact that serves as a tomb and a time capsule. Cameron's own words perfectly articulate this deep connection between the artistic and the real, noting that the deep ocean is the last frontier, full of myths and realities intertwined. His work demonstrates that the appeal of the Sunken Plateau is timeless, effortlessly translating from the pages of 19th-century novels to the most advanced digital cinemas of the 21st century. The inspiration drawn from these landscapes is beautifully diverse, appearing across every form of artistic expression. In music, the British rock band Led Zeppelin wrote The Ocean as a tribute to their sea of fans, but their broader musical aesthetic is filled with references to mystical, ancient lands and epic journeys, a thematic cousin to the saga of a lost continent. In classical music, composer Claude Debussy was famously inspired by the same Atlantis myth that captivated Verne, seeking to capture its mysterious, aqueous beauty in his compositions. The world of painting is rich with depictions of deluges and fantastic seascapes. The romantic and dramatic works of artists like Ivan Ayvazovsky portray the ocean as a sublime, powerful, and often destructive force, with waves that seem to swallow whole worlds. Even in video games, titles like Subnautica and BioShock build their entire narratives around the exploration and survival in mysterious, beautiful, and terrifying underwater environments, allowing players to personally experience the wonder and peril of these hidden realms. This enduring power lies in the Sunken Plateaus' unique ability to function as a multi-layered symbol. It represents the ultimate mystery, a blank space on the map that invites exploration and discovery. It embodies a profound sense of loss, a nostalgic elegy for a world that has passed, echoing our own anxieties about the impermanence of our civilizations in the face of climate change. And yet, it also symbolizes hope and resilience, the idea that even in the deepest, darkest abyss, life and stories find a way to persist and adapt. These submerged landscapes hold up a mirror to our own world, reflecting our deepest fears and our most aspirational dreams. We would love to hear which of these artistic interpretations resonates most with you. Is it the classic adventure of Verne, the cutting-edge visuals of Cameron, the epic soundscapes of rock and classical music, or the interactive worlds of video games? Share your favorite representation of a sunken or lost world in the comments below, and let us know why it captures your imagination. This rich dialogue between art and science is a vital part of the story, reminding us that our quest to understand these plateaus isn't just about data and drones. It's also about fulfilling a deep human need to tell stories about the wonders that lie just beyond our sight, a curiosity that now drives us to look forward and use our knowledge to shape what comes next. The same geological forces that drowned the sunken plateaus of the past are actively shaping the coastlines of our future. And by studying these ancient submerged landscapes, we are essentially reading a detailed blueprint of what is to come. This isn't about vague predictions, it's about using Earth's own history as a high-fidelity model to forecast the specific challenges that rising seas and shifting lands will bring. The data pulled from sediment cores on plateaus like the Agulhas or the Newfoundland Ridge provide the critical ground truth for the complex computer simulations used by climatologists. These models, which inform the dire projections in Intergovernmental Panel on Climate Change reports, rely on past events to validate their accuracy. When a simulation can accurately recreate the sea level rise and temperature shifts that occurred during the last major deglaciation, as recorded in those deep sea archives, we can have far greater confidence in its predictions for the year 2100. This transforms our understanding from a theoretical exercise into a data-driven forecast, revealing not just that change is coming, but how fast it will arrive and which areas will be most severely impacted. This powerful synergy between paleogeology and modern climate science allows us to generate startlingly precise scenarios for vulnerable regions around the globe. Consider the Sundarbans, the vast mangrove forest deltas straddling the border of India and Bangladesh. This World Heritage Site is home to millions of people and the last refuge of the Bengal tiger, and it is also one of the most climate-threatened places on Earth. The entire region is a low-lying, dynamic delta built from sediment deposited by the Ganges, Brahmaputra, and Meghna rivers. Geological studies of similar drowned river deltas in the past show a predictable pattern. As sea levels rise, saltwater intrudes further inland, killing off the freshwater vegetation that holds the soil together, leading to accelerated erosion and ultimately catastrophic land loss. Projections based on these historical analogues, combined with current rates of ice melt and subsidence, suggest that a 1-meter rise in global sea level, a very plausible scenario by the end of this century, could submerge nearly half of the Sundarbans. This would not only create an incalculable ecological disaster, but also displace countless communities, creating a severe humanitarian crisis. The fate of the Sundarbans is a microcosm for thousands of coastal cities and ecosystems worldwide, from Miami to Manila, all of which face a similar interplay of rising water and sinking land. This is where the insights of futurists and systems thinkers become essential. Science fiction author and visionary Dr. Kim Stanley Robinson, who meticulously researches climate science for his novels, argues that understanding Earth's history is key to navigating its future. His perspective underscores that our path forward cannot be charted by technology alone. It must be guided by a deep comprehension of planetary cycles and the long-term consequences of our actions. The story of the Sunken Plateaus teaches us that environmental change is often slow and inexorable until it reaches a tipping point, after which transformation is rapid and irreversible. This knowledge shifts the conversation from merely slowing down climate change to a more pragmatic, dual strategy of aggressive mitigation coupled with intelligent adaptation. It forces us to ask difficult but necessary questions about how we will live with the changes already set in motion. Do we invest in vast engineering projects, massive seawalls, tidal barriers, and pumped drainage systems to defend existing coastal megacities? Or do we begin the managed, strategic retreat from the most vulnerable shorelines, relocating critical infrastructure and communities to higher ground in a planned and equitable manner? Perhaps the answer lies in a third path, working with nature by restoring mangrove forests and coastal wetlands that act as natural buffers against storm surges and erosion, a strategy known as green infrastructure. The choices are monumental, and they extend far beyond engineering into the realms of economics, social justice, and political will. The economic cost of inaction will be astronomical, but the cost of adaptation will also be immense, raising profound questions about who will pay and how the burden will be shared between wealthy nations and the developing world, which often contributed the least to the problem yet faces the greatest risks. The geological record from the Sunken Plateaus offers no easy answers to these ethical dilemmas, but it does provide an irrefutable mandate. To prepare, we must first understand the past. This immense task of monitoring change and implementing solutions cannot be shouldered by governments and scientists alone. It requires a fundamental shift in public awareness and participation, inviting everyone to contribute to the collective effort of building a resilient future. But for all the advanced technology and grand international efforts, one of the most powerful resources in understanding our planet's sunken secrets is not found in a lab or on a research vessel. It's found in the collective curiosity of people everywhere. The quest to map and protect these lost highlands is no longer confined to a small group of experts. Thanks to the rise of citizen science, anyone with an internet connection can now become an active explorer, contributing directly to groundbreaking oceanographic discovery. This movement harnesses the power of the crowd, turning the monumental task of analyzing vast datasets into a manageable, collaborative effort that accelerates research at an unprecedented pace. Online platforms have become the new frontier for public participation, offering a digital portal to the deep sea. One of the most impactful initiatives is Zooniverse's Seafloor Explorer project. Here, researchers upload millions of never-before-seen images captured by autonomous underwater vehicles gliding over the ocean floor. Volunteers from around the world are then guided through a simple process to help classify what they see. Is this image sandy, rocky, or covered in seaweed? Can you spot any animal life like fish, crabs, or sea stars? This might seem like a small task, but the collective impact is staggering. By having thousands of eyes review this visual data, scientists can process information in weeks that would take a single researcher years, rapidly building a comprehensive understanding of the biodiversity and composition of these hidden landscapes. Each classification is a vital data point, helping to identify critical habitats, map the extent of vulnerable coral communities, and even spot anomalies that could lead to entirely new discoveries. This model of public involvement extends far beyond image analysis. Other innovative projects invite participants to help analyze sonar data, identifying interesting features like potential shipwrecks or underwater landslides on newly mapped sections of seafloor. There are also initiatives focused on tracking present-day changes, such as Coast Snap, where anyone visiting a shoreline can use a simple smartphone mount to take a standardized photo of the coast, contributing to a global database that monitors beach erosion and accretion in near real time. This creates a living record of how our coastlines are responding to rising sea levels and changing weather patterns, providing invaluable ground truth data that complements the satellite views of sunken prehistoric shores. The underlying principle of all these efforts is a powerful and transformative one: democratizing discovery. When individuals are invited to participate in the scientific process, they develop a deeper, more personal connection to the subject matter. Primatologist and conservation icon Dr. Jane Goodall, whose own groundbreaking work has long inspired public engagement with science, perfectly articulated this profound shift in perspective, noting that when people feel connected to discovery, they become stewards of the planet. This connection transforms abstract environmental concerns into tangible, personal involvement. The volunteer who identifies a rare sponge on the Blake Plateau isn't just playing a game, they are contributing to the case for its protection. The family that regularly contributes a beach photo becomes invested in the health of their local ecosystem. This sense of ownership is the bedrock of lasting conservation ethic. For those inspired to get involved, the pathways are more accessible than ever. Beyond joining online citizen science projects, supporting organizations dedicated to ocean literacy is a tremendous help. Institutions like local aquariums, marine sanctuaries, and non-profits like the Ocean Conservancy work tirelessly to translate complex science for the public and advocate for policy changes. On a personal level, the choices we make every day ripple outward to impact these hidden worlds. Reducing our carbon footprint directly addresses the ocean acidification and warming that threaten deep-sea coral ecosystems. Making sustainable seafood choices helps alleviate the pressure of deep-water fishing. Minimizing single-use plastic reduces the pollution that eventually finds its way into the deep ocean's food webs. Every informed action, no matter how small it seems, is part of a collective wave of stewardship. This growing public engagement is crucial because it creates a well-informed constituency that can advocate for the protection of these fragile places. However, this very wave of popular interest can sometimes carry with it misconceptions and simplified narratives. As we all become more connected to the story of Earth's sunken past, it becomes equally important to ground our enthusiasm in evidence, to separate the compelling wonders of natural geology from the seductive allure of pseudoscience. The allure of a lost city like Atlantis is powerful, painting a picture of a sophisticated civilization swallowed in a single, catastrophic day and night. It's a compelling narrative, but when we apply this myth to the actual sunken plateaus we've been exploring, the story quickly diverges from Hollywood drama to the more patient, yet equally astounding drama of geology. One of the most persistent misconceptions is that every large, submerged structure must be a remnant of some human-built metropolis, a fallen empire waiting to be rediscovered. The reality is that while these plateaus may have hosted life, even human activity in their shallower days, their formation and submersion are the work of planetary-scale forces operating on a timeline that makes human history look like a fleeting moment. They are not ruins in the archaeological sense. They are natural wonders, their history written in basalt and sediment, not carved stone. Another common myth that often surfaces is the idea that these sunken lands could suddenly re-emerge, bursting forth from the waves in a spectacular geological event. This image is fueled by stories of volcanic islands appearing, but the scale and process are entirely different. The formation and subsidence of a massive plateau like the Kerguelen or Zillandia is a saga that unfolds over millions of years. The forces involved isostatic adjustment, thermal subsidence, and eustatic sea level change are incredibly slow and relentless. Think of it not as a light switch being flipped, but as a dial being turned with imperceptible slowness over eons. A volcanic island might emerge quickly from a single eruption, but an entire continental fragment sinking or rising is a process of profound patience. The crust bends and sinks under immense weight at a rate of perhaps a few millimeters per century, a pace that is completely undramatic from a human perspective but utterly transformative over geological time. To navigate this landscape of fact and fiction, we need a guide grounded in evidence. Astronomer and science communicator Dr. Phil Plait, known for his work debunking bad science, offers a crucial principle that applies perfectly here. He reminds us that science thrives on curiosity, but it must be grounded in evidence. This is the essential balance. It's wonderful to be curious about the possibility of ancient civilizations or sudden cataclysms, but that curiosity must be channeled into a rigorous examination of the physical evidence. The scientific process requires that claims be tested against observable data, and for sunken plateaus, that data is overwhelming. Core samples show continuous layers of marine sediment, not the jumbled rubble of a sudden collapse. Radiometric dating of volcanic rock reveals ages in the tens of millions of years, not thousands. The evidence consistently points to a long, gradual process of descent. A classic example of how a natural formation can be misinterpreted is the case of the Bimini Road off the coast of the Bahamas. For a time, this linear arrangement of limestone blocks was heralded by some as a paved road or wall from the lost city of Atlantis. However, geological analysis revealed the truth. It is a superb example of a natural formation called beak rock. This type of rock forms in the intertidal zone when sand and shell fragments become naturally cemented together by calcium carbonate. Over time, as sea levels rose or the land subsided, this beak rock fractured along its natural joints, creating the appearance of neatly arranged rectangular blocks. It's a fascinating geological feature, but it is not an archaeological one. This case underscores the importance of consulting experts from the relevant fields, in this case, geologists, not speculative historians, to correctly interpret what we find on and under the seafloor. This practice of healthy skepticism isn't about shutting down wonder, it's about deepening it. By dismissing the simplistic myth of Atlantis, we open ourselves up to the far more grand and complex true story written in the geology of our planet. The genuine narrative of a continent like Zillandia, stretching and thinning for millions of years before finally succumbing to the waves, is an epic of incredible scope. It invites us to think on a different scale, to appreciate the slow, powerful forces that truly shape our world. This disciplined approach to evidence ensures that our fascination is directed toward the real mysteries, like the exact timing of submergence or the full extent of biodiversity these plateaus supported, rather than chasing phantoms. This commitment to evidence-based inquiry is what allows us to build a reliable understanding of our planet's past, and it is this same rigorous, cross-disciplinary dialogue that forms the foundation for the entire field of studying these lost worlds. Truly understanding a sunken plateau is like trying to solve a magnificent, multi-dimensional puzzle where the pieces are scattered across different universes of knowledge. You cannot hope to see the complete picture by looking through a single lens. The story of these lost worlds is written in layers of rock, layers of ice, layers of biological adaptation, and layers of human memory. To read it, you need a team of translators, each fluent in their own specialized language of discovery. This is where the real magic happens, at the vibrant, often messy, intersections between disciplines. A geologist can use radiometric dating to determine that a basalt layer from the Kerguelen Plateau is 100 million years old. A paleontologist examining a core sample from that same rock might then identify a fossilized pollen grain from an ancient conifer tree that only grew in a cool, temperate climate. Suddenly, the cold data point transforms into a scene, a volcanic highland forest shrouded in mist. Meanwhile, a historian analyzing Tamil Sangam literature might find an ancient poem describing a vast land to the south that was consumed by the sea, a story that echoes the geological timeline of subsidence. Independently, these are fascinating facts, but when woven together by researchers willing to listen to each other, they become a powerful, unified narrative of a lost continent and its impact on both the planet and its people. This collaborative spirit is the engine behind the most ambitious deep-sea research initiatives in the world. Programs like the Integrated Ocean Drilling Program, now succeeded by the International Ocean Discovery Program, or IODP, are floating universities of interdisciplinary science. A single expedition aboard their drilling ship, the Joyd's Resolution, is a masterclass in cooperation. On board, you'll find sedimentologists meticulously describing the texture and composition of a freshly pulled core, trying to discern if it was laid down in a deep marine environment or a shallow coastal lagoon. In the next lab, paleomagnetists are studying the orientation of magnetic minerals in the rock, which act like a fossilized compass, recording the Earth's magnetic field at the time the sediment was deposited and providing another method for dating. Down the hall, microbiologists might be sampling the core under sterile conditions, searching for extremophile bacteria that have been living in the deep rock for millions of years, which could reshape our understanding of the limits of life itself. The goal is not for each scientist to simply grab their own sample and go home. It is to combine all these disparate lines of evidence, the chemical, the physical, the biological, to reconstruct a full-bodied portrait of an ancient environment. They are collectively building a time machine, one data point at a time. This necessity for integration is something historian of science Dr. Naomi Orskes has powerfully championed. Her assertion that the biggest questions demand we break down academic silos is not just an academic opinion, it is a statement of practical necessity. The most profound mysteries of our time, like understanding past climate change or the drivers of mass extinction, are simply too large for any one field to tackle alone. They exist in the borderlands between specialties, and solving them requires a shared vocabulary and a shared purpose. A brilliant geophysicist might model the thermal subsidence of a plateau with stunning accuracy, but without the input of a biologist, they might completely overlook how that sinking process created isolated seamounts that became evolutionary crucibles for new species. The silo might produce a lot of grain, but it takes an open marketplace of ideas to bake the bread. A perfect case study of this interdisciplinary dance is the ongoing research into the Amazon cone, a massive underwater fan of sediment that pours out from the mouth of the Amazon River and spills across the seafloor. To understand this one feature requires a symphony of expertise. Sedimentologists study the core samples to trace the source of the sediments and the powerful currents that carried them. But their work is amplified by ecologists, who examine how this constant rain of organic material from the world's largest river supports a unique and largely unexplored deep-sea ecosystem in the otherwise barren abyssal plain. Climatologists then join the chorus, analyzing the same sediment layers for clues about the Amazon's rainfall history over millennia, which is directly tied to global climate patterns. They can correlate layers rich in certain plant fossils with periods of increased precipitation, building a history of the rainforest's expansion and contraction. This isn't just three separate studies happening to use the same mud. It's a single, coherent investigation into how a river, an ocean, and a climate system interact, with each expert providing a crucial movement in the larger symphony. The resulting understanding is so much richer and more valuable than the sum of its parts. This integrated approach does more than just advance science. It fundamentally changes how we see our world. It replaces a fragmented, compartmentalized view with a holistic one, revealing the beautiful and complex connections between the solid Earth, the fluid ocean, the living biosphere, and human culture. It teaches us that a shift in a tectonic plate can alter ocean currents, which changes global climate, which forces species to adapt or migrate, which in turn influences the spread and development of human civilizations. Appreciating this interconnectedness is the first step toward a more nuanced and responsible relationship with our planet. It moves us from seeing the environment as a collection of resources to be managed, to understanding it as a deeply intertwined system of which we are an active part. This profound shift in perspective, from isolated facts to woven knowledge, naturally leads us to a more personal question, one that connects this grand planetary narrative directly to our own lives and choices. This journey into the depths, exploring these lost worlds that once scraped the sky, might feel like a story from another planet, a distant drama of geology and time that has little to do with our daily lives. But the truth is, the story of the Sunken Plateaus is intimately, powerfully connected to you, to the ground under your feet, the air you breathe, and the future you will help shape. Understanding these hidden landscapes does more than satisfy our curiosity. It fundamentally reshapes our relationship with the planet we call home. It fosters a profound appreciation for Earth's breathtaking dynamism, revealing that our world is not a static stage upon which life simply plays out, but a vibrant, ever-changing entity with its own deep, powerful rhythms. This knowledge redefines our place within this system. We are not separate from nature looking on from the outside. We are participants, living on a thin, vibrant crust that is constantly in motion, both supporting us and responding to forces of unimaginable scale. This perspective can transform our attitude toward environmental stewardship from a sense of abstract duty into a deeply personal commitment to safeguarding the delicate, miraculous balance that allows us to exist. We can see this connection playing out in real time along coastlines across the globe today. The challenges faced by the ancient inhabitants of Doggerland or the Sunda Shelf are not relics of a forgotten past. They are a mirror to our own emerging reality. Consider the residents of the Solomon Islands in the Pacific, where several low-lying islands have already vanished completely beneath the waves, forcing entire communities to abandon their ancestral homes and become some of the world's first climate refugees. Or look to the bayous of Louisiana, where a combination of sea level rise and land subsidence is causing the loss of a football field of wetlands every 100 minutes, erasing a critical buffer that protects cities like New Orleans from hurricanes. These are not future scenarios, they are present-day events, modern echoes of the great retreats forced upon our ancestors. Their stories are a sobering reminder that the forces that drowned continents are not spent, they are ongoing, and our actions are now a key part of that geological equation. The choices we make about energy, consumption, and policy today are actively writing the next chapter in the story of which lands will be preserved and which will be surrendered to the sea. This forces upon us a series of deeply personal and reflective questions. How does knowing this long, deep history of a changing Earth alter your perception of the current climate crisis? Does it make the threat feel more real, more grounded in the undeniable logic of geology, rather than just a political or scientific debate? And perhaps more importantly, what kind of legacy do we wish to leave for the generations that will follow us? Do we want our chapter in Earth's story to be one where we understood these powerful forces and chose to ignore them, accelerating a period of great loss and disruption? Or will it be a chapter where we, armed with the hard-won knowledge of the past, chose a path of wisdom, resilience, and stewardship, working to preserve the stability and beauty of this world for our children and grandchildren? The answer to that question will be written in the sediment cores that future scientists will one day pull from the ocean floor, a permanent record of our choices. This call to mindful action is beautifully encapsulated in the timeless words of naturalist and philosopher John Muir, who over a century ago observed that when we try to pick out anything by itself, we find it hitched to everything else in the universe. His insight is the ultimate lesson of the Sunken Plateaus. You cannot isolate the burning of fossil fuels from the acidification of the deep ocean that is dissolving coral skeletons on the Blake Plateau. You cannot separate a policy decision made in a distant capital from the fisherman in the Sundarbans who loses his livelihood to saltwater intrusion. You cannot disconnect the plastic bottle discarded in a Midwestern city from the microplastic particle found in the gut of a creature living in the crushing darkness 4,000 meters down. The story of these lost highlands is the ultimate proof of this cosmic hitchiness. A volcanic eruption in the Indian Ocean millions of years ago influenced ocean currents, which shaped climates, which directed the migration of species, which ultimately influenced where and how humans built their civilizations. We are all hitched to those sunken worlds, and we are all hitched to each other, bound together in a vast, interconnected web of cause and effect that spans across deep time and the entire globe. Recognizing this interconnectedness is the first, most crucial step toward building a more thoughtful and sustainable future, a responsibility we all share as temporary passengers on this dynamic, ever-evolving planet. And so our journey across these sunken worlds, these lost highlands that once touched the sky, draws to a close, but the story itself is far from over. We have ventured from the fiery volcanic origins of these geological titans to the silent, sediment-cloaked depths where they now reside. We've seen how they served as bridges for ancient life, as homelands for our ancestors, and as the inspiration for myths that have haunted humanity for millennia. We've marveled at the pioneering spirit of the early oceanographers who first mapped these invisible realms, and at the cutting-edge technology that now allows us to paint them in breathtaking detail. Through the lens of these drowned landscapes, we have witnessed the profound and inseparable link between the solid earth, the shifting seas, and the relentless, adaptive spirit of life itself. The true power of this story lies in its incredible relevance. These sunken plateaus are not just relics, they are active, living records. They hold the keys to understanding our planet's climatic past, providing the hard data that validates our models of future sea level rise and global warming. They remind us that change is the one true constant of our world, a force of both creation and destruction that has shaped continents and cultures alike. But within that narrative of change is a parallel story of breathtaking resilience, the resilience of ecosystems that find a way to thrive in the eternal darkness, and the resilience of humanity, forced to adapt, migrate, and innovate in the face of rising waters, both in the ancient past and in our emerging present. This duality is the overarching theme, a planet in constant flux and the enduring life that finds a way to persist, as the renowned oceanographer Dr. Robert Ballard so eloquently put it. The ocean is the largest museum on Earth, and we are just beginning to read its collections. His words are a perfect summation of where we stand today. We are the first generation to hold the keys to this vast, submerged museum, to truly begin deciphering the stories written in its mud and rock and fossilized life. With this knowledge comes an immense responsibility, a responsibility to explore with curiosity but also with care, to seek out resources with ambition but also with ethics, and to protect these irreplaceable archives of our planet's history for all the generations to come. The next chapter of this story is yours to write. Your curiosity is the most important tool of exploration we have, so we encourage you to keep diving deeper. Subscribe to this channel for more journeys into the world's greatest mysteries. Share this video with someone who marvels at the hidden wonders of our planet, because spreading awareness is the first step toward fostering protection. And most importantly, we want to hear from you. Down in the comments, tell us what fascinates you most. Is it the lost civilizations, the deep sea discoveries, or the profound lessons these sunken worlds hold for our future? The conversation, just like the ocean, is deep and waiting for your voice. Thank you for exploring these lost highlands with us. Until our next adventure into the unknown.